So
ready?
Yes.
Okay. So a new topic for those interested in the Riemann hypothesis. So the Riemann Zeta-Function, Riemann hypothesis, in connection with the Möbius function that we discussed in class. But since you just mentioned or asked me a minute ago after we turned off that video, what grade I gave that student, it was the lowest passing grade. Well, it was correct. 5 plus 7 was 12.
Oh, I know, but 5 plus 7.
5 plus 7. So if you can pass with that, then of course you can pass our class as well. Because this is going to be easy. Okay, Riemann Zeta function, not part of the exam or any exams. So it goes like this. We take a complex plane where we have numbers, but forget about the complex numbers for the moment. I have 0 here, 1 here, I there, and so on. Look at this vertical line. These are numbers that have this form: 1 plus I, 1 plus 2I, 1 plus 3I, 1 plus half I.
AI plus 1/2.
So 1 plus any real number times I. Okay. That's a Greek letter that I don't know how to make, but let's say this is the zeta. Zeta of S. For any complex number S where the function is defined like this. It's defined as a series. 1 plus 1 over 2 to the S. And if I don't like complex numbers, let's work with real numbers only. Today. 1 over 3 to the S, 1 over 4 to the S, 1 over 5 to the S, and so on. All the integers, all the positive integers I take, I raise them to the S power, and I invert this. So for instance, zeta of 2 is 1 plus 1 over 2 squared plus 1. So in other words, 1 plus 1 over 9 plus 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over the next square is 25 plus 1 over 36 and so on. This is a convergent series, which we can see in calculus classes, that you can bound this, the sum, if you think about it. You can bound the sum that looks like 1 over n squared. The sum goes from 1 to infinity. That's the short form notation for this infinite sum. You can bound this and say this is less than or equal to 1 plus maybe the integral from 1 to infinity 1 over t squared dt, something like that. Because you can bound this because if you think about this, first of all, you can compute the integral.
Yes.
Exactly.
Yes.
In calculus.
Minus 1 by t.
All right. You can find an antiderivative, and then you can compute the values at 1 and at infinity, and infinity is 0. But from calculus, we know that what the meaning of this is this is equal to the area under the graph of the function.
It'll be 1.
So,
It'll be 1.
1, 2, excuse me a second. Whatever the area is, we don't care about the area.
Yes.
The area is some finite area that you can compute. If you say it's 1, it's 1. Now, I look at this function. It looks like this, 1 over t squared. F of t is 1 over t squared. The total area can be computed and it's bounded. It's not infinite. That's what I'm saying. The area is not infinite. Not an infinite area under the graph. So the sum of areas of these rectangles that I can form here that are under the graph is also finite because it's smaller than that. Now, what's the area of these rectangles? From 1 to 2, but what are the values? F of 1 is 1, and f of 2 is 1 over 4. So this length is 1 over 4. So this area is 1 over 4. The next area is 1 over 9. The next area is 1 over 25, if you look at this, because these are the consecutive values of this. F of 2, f of 3, f of 4, f of 5, 1 over 2 square, 1 over 3 square, 1 over 4 square, and so on. So if you look at all these areas of these rectangles, you get these numbers. So this is anyway less than the area of the integral. The area of the integral, the area under the integral. So the actual integral from 1 is less than the integral from 1 to infinity of 1 over t squared dt. Okay, what's the actual integral now that we talk about calculus?
1.
A1, and you agree with that?
One.
Yeah, well, negative 1, I think.
Negative
No,
1,
sorry,
but
sorry,
here is 1.
One.
Okay, let's see. Some calculus. What's an antiderivative of 1 over t squared?
Minus 1 by t.
Minus 1 by t, so minus 1 over t. I put here, but I take this, the fundamental theorem of calculus,
Yes.
and move here.
Yes.
Okay, that's 1, and then infinity.
0
Now 1 over
plus-
infinity is 0, doesn't bother us. But at t equals 1 is 1 over 1, so it's 1.
Yes.
But minus 1,
No. Minus of
aha,
1.
fundamental theorem of calculus, because it's the value here at infinity minus the value at 1. But the value at 1 is a minus 1, so minus minus gives a plus.
Yes.
So this actual integral is, of course,
I
1.
did it yesterday. Yeah.
1. So the sum of these numbers is less than 1. In particular, the series is convergent.
Yes, sir.
Why do I put a 1 plus that? Because they start here with 1 over 4 plus 1 over 9. The Riemann Zeta-Function starts with a 1. So 1 plus this. So the sum of 1 over 4 plus dot, 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 dot is less than 1, we found. So the whole thing is well defined. Zeta of 2 is well defined. And it's a number that's less than 2. Because this sum we just saw is less than 1. Not only the series is convergent, but it's less than 2. 1 actually proves that this number is, excuse me, that this number is actually equal to pi squared over 6. It can be computed. The sum of inverses of squares of positive integers is pi squared over 6. Okay. So this is, so we compute, it's pi squared over 6, whatever it is, and that's the value of the function when s is equal to 2. So the function is defined in the complex plane, and when s is equal to 2, its value is whatever the value is. Okay, now, Riemann, the so-called Riemann hypothesis is about the following question. For what values of s, zeta of s is 0? Can it be 0? Let me remove this. For what values, or which values of s is zeta of s 0? Question mark. And I look at this thing, and it's 1 over 2 to the s, 1 over 3 to the s. I cannot see how this thing can be 0. At least when s, because these are positive numbers. How can I add positive numbers and get 0? So, first of all, we computed or we discussed that this is convergent when s is larger, when s is 2. But in fact, for any s larger than 1, the series is well defined, zeta of s, and it's convergent and it's bounded by an integral with 1 over t to the whatever the number s is instead of 2, that we also can compute. So for all s larger than 1, I have 1 here, for all s larger than 1, zeta of s can be computed in this way, and it's never 0, because it's a sum of positive numbers. But how can that be then that for if I put an s that's a complex number s may have a form like a real number a plus another number times I. We know from our experience with computations when we write a number as sum of two squares and when we use complex numbers, I squared is -1, so in computations can give some negative numbers there. So when I take an s that's complex, when I take 2 to the s, whatever that may be, it's another complex numbers, but its real part and imaginary part are complicated. I don't know if the real part or the imaginary part or both are positive or negative. And when we add all these numbers, it could be in principle that the sum of all these real parts is 0 and the sum of all these imaginary parts is 0, so that the total number is, as a complex number, 0. How unlikely this might be the case. Now, this is an introduction to this, but what happened is that Euler, we discussed about his work on Euler's theorem and so on, but he did many other things. One of the things is that he actually considered this function, not Riemann. Euler worked with this before Riemann. People call this the Riemann zeta function. What happens is that Euler considered this function. I don't mean that, I don't say that he used this same notation, but he did consider this function 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s and so on. And he worked only with s larger than 1, real numbers. He knew, of course, that something bad happens when you let s decrease to 1. We cannot compute zeta of 1. Zeta of 1. It's not defined. It would be 1 plus 1 over 2 plus 1 over 3 to the 1, 4 to the 1, 5 to the 1, 1 over 3, 1 over 4, and so on. This is what we call in
infinity. Divergent.
How we call this in calculus?
Harmonic series.
Harmonic series. And this is divergent. Okay.
Very slow.
And to show that, simple exercises in calculus, how you show that this is divergent? You show that 1 over 3 plus 1 over 4 is larger than 2 over 4, which is 1/2. So these two together is larger than 1/2. The next 4 together, the sum of them is larger than 1/2. The next 8 together, the sum is larger than 1/2, and so on and so on. So this grows beyond any bound. The sum is divergent. So zeta of 1 cannot be defined. And because this diverges, what Euler noticed is that then if you take s to be larger than 1 but approach 1, then of course the limit
Approaches
of zeta of s as s approaches 1 but decreases to 1, it's plus infinity. The limit is infinity. Now, from the right, s approaches 1, zeta of s goes to infinity. That's how we write it. Or some people write it like this. They say zeta of s goes to infinity as s decreases to 1. Keep this in mind. Now, Euler discovered what people call now the Euler product for the Riemann zeta function. So his name is still attached to nowadays to this function, to the zeta function. Euler product. What he did is the following. He showed that this can be written as a product, as follows. Zeta of s, zeta of s is equal to the following. 1, he observed this, and he's using nothing but the fundamental theorem of arithmetic that we discussed in class to see this thing. He takes powers of 2 first. 1 plus 1 over... Now, he does something of the following form. Let me simplify this. I remove this for the moment. And let me simplify a little bit this. So, I take zeta of s and I multiply by 1 minus 1 over 2 to the s. I multiply by zeta of s, see what happens. What happens is, I get 1 minus 1 over 2 to the s. S doesn't bother me, it's just a variable here. 1 minus 1 over 2 to the s times zeta. But zeta is 1, plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, all the positive integers. 1 over 5 to the s, 1 over 6 to the s, and so on. And when I multiply these things, I get a 1 times each one of them is 1. Is that number, 1 plus 1 over 2 to the s, 1 over 3 to the s, 1 over 4 to the s. If you, as you said, if you two are interested in our 5 to 1, that's how we start. We start exactly I would start it like that with the Riemann zeta function and with the Euler product, and because I quickly want to show that there are applications. I want to give a new proof that there are even many prime numbers by using Riemann zeta function. That's what Euler did.
Okay.
We have a proof due to Euclid there are infinitely many, but this gives a bit more. It tells us about how many we have. Now let's see. Like for instance, there are more prime numbers than squares. Both of them are. We have infinitely many primes, infinitely many squares, but still there's more primes than squares in the sense that if I stop anywhere I want, that from 1 to 1,000,000 or from 1 to 1,000,000,000, and I look at how many squares I have, how many primes, I have many more primes than squares. That follows from this proof, for instance, in a moment. But let's see this. 1 plus 1 over 2 plus 1 over 3 to the s, 1 over 4 to the s, and so on. 1 over 5 to the s, 1 over 6 to the s, and so on, when you multiply by 1. Now, when I multiply these numbers by 2, I get, and I have a minus. 1 over 2 to the s times 1 is, 1 times minus 1 over 2 to the s is minus 1 over 2 to the s. I'll just write it under this, because I want to cancel this in a moment. Then I have this times the other one is 1 over 2 to the s times 1 over 2 to the s is 1 over 4 to the s. Again with a minus, minus 1 over 4 to the s. Then I take the next one, multiply by this is 1 over 6 to the s. That is 1 over 6 to the s. And so on. All these appear with minus in front of them and will cancel the corresponding terms. So we are left with just odd numbers to the same power s. Odd numbers. The conclusion is that if you take 1 minus 1 over 2 to the s and multiply by the Riemann zeta function, this simply removes all the multiples of 2 in the denominator. So this gives 1 plus 1 over 3 to the s plus 1 over 5 to the s plus 1 over 7 to the s and so on. 1 over 9 to the s. Let's see now. Now, next, Euler multiplies this by 1 minus 1 over 3 to the s. So he has 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s times zeta of s, and is equal to, okay, let's multiply this by 1 minus 3 to the s times the previous one. 1 minus 1 over 3 to the s times the previous one times this. 1 plus 1 over 3 to the s plus 1 over 5 to the s plus 1 over 7 to the s and so on. So this equals now, I multiply by 1, I get all odd numbers, 3 to the s, 5 to the s, 7 to the s and so on. And then minus this thing with 3. 3 times 1 is 3, so minus 1 over 3 to the s, it cancels this. Then I have 3 to the s times 3 to the s is 9 to the s, minus 1 over 9 to the s. It cancels plus 1 over 9 to the s from there, and so on. This will remove the multiples of 3 that were left here, that were not removed already. So we're left with just 1, okay, there was zeta for s larger than 1. We're left with just 1 over 5 to the s plus other things. And then Euler continued in the same way to remove all the other numbers that are there.
Is this like because it's modular too? So because they're all co-prime essentially, because that works. So you can cancel out all of them.
So we can cancel. Yeah. So he concluded the following: that if you take zeta of s and you multiply by 1 minus 1 over 2 to the s by then times 1 minus 1 over 3 to the s, and then we're left with 5. There's no reason to put a 1 minus 1 over 4 to the s. It's the next prime number that appears. 1 minus 1 over 5 to the s times 1 minus 1 over 7 to the s and so on. If you stop after finally many steps, you still have numbers there. You always have a 1 plus some numbers that are not removed. So you have to take a limit here in order to remove everything except for this 1 and to be a 1. So if I write that this equals 1 right now, it's not correct. I should write it as a limit. So in other words, this thing is a product like a series when we have infinitely many terms in a series in calculus. Now we have infinitely many factors in a product. So only if I take all those infinitely many factors in the product, then we get a clean one. If I stop after any finite number of steps, I don't get one. I get one plus some other numbers that are not removed. Some numbers that are not divisible by any of these 2, 3, 5, or 7. Okay. So now he concludes from here that, let's recall what we saw before. What we saw before was that zeta of s tends to infinity as s decreases to 1. Okay, that's one thing. The other thing is zeta of s is given as a definition as 1 plus 1 over 2 to the s plus 1 over 3 to the s plus blah, blah, blah. For all s real numbers that are larger than 1, keep real, no complex. And another thing is this infinite product, which is nowadays called Euler product. So zeta of s is equal to the following product. It's 1 over, okay, how am I write it? It's an infinite product over all the primes, p prime, of 1 over 1 minus 1 over p to the s. It's like that. And this is also for all s larger, for any fixed number s larger than 1. This is an infinite product, but the product converges to a number. That's exactly zeta. Why? Because if you recall what we had before, I erased, it was zeta multiplied by all these numbers. There was 1. So zeta itself is 1 over this thing. Okay. Finished?
Let's stop.
Let's stop. Okay.